So hello everyone, welcome to the sixth lecture on Introduction to Geosynthetic Applications. So in yesterday's lecture we discussed about we solved a problem related to the reinforced soil wall. So where we used a geogrid to reinforce the soil wall. So that problem we solved. So with that we completed all the three types of problem, that is reinforcement with geosynthetic, that is geotextile, then geogrid, and also steel. All right, and after that, we started the topic of bearing capacity improvement with geosynthetic reinforcement, right? So we started that topic, and we are going to continue with that in today's lecture. First of all, we are going to cover and finish that up, and after that, for the remaining time that we have, we are going to study the uh, accelerated consolidation using PVDs. Okay, so that part we are going to do, and after that, in tomorrow's session, we will end the course by studying the remaining two topics, that is the drainage and filtration using geosynthetic, and then we will study a little bit about the liners. Okay, so let us start today's session. So we already discussed this thing in yesterday's session, right? So when we use any reinforcement, geosynthetic reinforcement for bearing capacity improvement, the things that we have to keep in mind is that the depth of the first layer of reinforcement, right? That is U. This U depth is very important. Okay. So there are three types of failure, or three situations where this reinforcement might not work, right? So the first situation is when the depth of the placement is too high. That is, the U by V is greater than 2 by 3. And if the U by V is greater than 2 by 3, then what happens? The shear failure happens. The shear surfaces actually develops above the reinforcement. So with that, there is no interaction with the reinforcement, and so there is no bearing capacity NSP. So what we have to ensure? We have to ensure that the U by V is less than, always less than 2 by. Now, after we ensure U by V less than 2 by 3, there are other two things also that we have to ensure. So first, you have to ensure that there is no pull out. Okay, the reinforcement does not pull out during the loading process, right? So we have to provide sufficient anchorage. Okay, sufficient anchorage length or embedment length, so that the reinforcement does not pull out. So generally this happens when the number of reinforcements are less than 2 or 3, or the reinforcements are less. So you need to provide adequate number of reinforcement, and also adequate length of reinforcement should be provided to prevent this pull out failure. And the third case is that when you have ensured that there are adequate number of ties, there's adequate number of reinforcement layers, say greater than 4, and the ties are also long, but you forgot to ensure that you did not ensure that the strength of the reinforcement is sufficient to take the load that is done, right? So you need to also ensure that the strength of each reinforcement is adequate. Else what will happen? These reinforcements will rupture. Okay, like this, at this point it's gonna rupture. Okay, so these are the possible scenarios. So till this much we had discussed in yesterday's class, so we are going to continue this. Now what we are going to do is see is that the theoretical analysis of reinforced foundation as per Binkett and Lee 1975. Okay, so the Binkett and Lee, they researched did some initial research on this, and they had published a theoretical analysis procedure. So how we should actually design this reinforcement. Now you can see here in this plot we have plotted the bearing capacity ratio versus the depth ratio. Depth ratio is U by V, and then we have plotted the bearing capacity ratio. Okay, so bearing capacity ratio is nothing but this here is Q by Q naught. So Q is the new bearing capacity that we get after we put the reinforcement, and Q naught is the bearing capacity without the reinforcement. Okay, so Q by Q naught. So greater than 1 means there is some bearing capacity improvement. Okay, so here for various angle of friction angle values, the plots are there for bearing capacity versus depth. So we see that as the depth ratio U increases, what happens? The bearing capacity ratio reduces. So how you can see that? So say for one depth ratio, let us see. So for depth ratio 1, you are seeing that for 42° phi, we are getting a bearing capacity ratio somewhat here. Okay, now if you reduce the depth ratio, let us go to depth ratio here. So then you will see that for the same 42° curve, we are getting a higher bearing capacity ratio. So this means first, if U is higher, then the bearing capacity ratio reduces, right? Okay. Okay, so these bearing capacity values are actually for mode 1 failure. It is this okay, U by V greater than 230. Now, during any design, the bearing capacity ratio must be ensured around 3 to 4. So when we ensure that the bearing capacity is between 3 to 4, we ensure that the cost economics that is involved, that is the cost that we have to incur for placing the reinforcement is justified. Okay, that means you have two options, right? So either you can use a deep foundation, or you can increase the foundation size, or whatever you can do, right? So these are the things that are there. The third option that we have is that we apply this reinforcements. So at least the bearing capacity ratio, if we when you are using the reinforcement, should be 3 to 5, then only the cost involved in placing these reinforcements will be justified. Yes. So here the bearing capacity ratio is actually defined. The bearing capacity ratio, as I said before, is Q by Q naught, where Q is the footing pressure on reinforced foundation, and Q naught is the footing pressure on unreinforced foundation, both measured at the same setting. The bearing capacity ratio was found to be in the range from 1.5 to 4, depending on the settlement criteria and density of reinforcement. Now, let us see the mechanism, the failure mechanism that is associated with this. Okay, so we are seeing here. So here we have a footing, right? Footing A dash A. That this is our strip footing. Okay, and the stress distribution below the strip footing is actually shown to. Okay, so surfaces A prime, C prime, and AC represent the locus of maximum shear stress. Okay, so these A prime, C prime, and AC, these are the locus of the maximum shear stress. So when you are loading a surface, okay, when you are loading a surface, what happens at any depth, okay, say at this depth, what happens is that the vertical stress varies like this, right? At the center, it's maximum. Okay, the center is maximum, and as we move away from the center, the stress reduces. So this is the vertical stress variation. And what happens to the shear stress distribution? The shear stress is actually something like this. Okay, so it is minimum at the center, and it is maximum at some point beside the center. Okay, this one. So the point at which the shear stress is maximum from the center, that point we mark as x naught. You can see here. Okay, that point we are marking as x naught. And at all the depths, at various depths, you will have various points at which the shear stress will be maximum. So the locus of all those points, if you join all those points, you will get you can make a line. So these are those lines, A prime, C prime, and AC. So along these lines, A prime, C prime, and AC, actually there are chances of rupture of the reinforcement. That is the points at which the shear stresses are maximum. Okay, so at those points, there are high chances for the reinforcement to rupture. Okay, a variation of vertical pressure and shear stress were looked discussed now. So as load increases, the soil moves down laterally and away. So obviously, as the load increases, the soil moves down and it also laterally moves out. At the center line, the shear stress. Okay, so this is this dotted line here. Okay, these dotted lines. The shear stress is zero. Okay, so at the center line, the shear stress is zero, and the vertical stress here is the maximum. Okay, the vertical stress are maximum at or any level. Okay, that is at any depth. As we move laterally, the shear stresses reaches maximum and reduces zero. The vertical stress keeps reducing. So whatever we discussed here. Okay. So for analysis, no rotation is considered. Now, from Bosenick's theory, what we can write? We can write the equation of vertical stress. Okay, vertical stress below a loading Q at any depth Z, at any level Z, we can write the expression for vertical stress as well as we can write the expression for shear stress, right? We can write the expression for shear stress, also the expression for vertical stress. So both these vertical stress and shear stress are functions of both Z, that is the depth, and also the lateral coordinate, right? This from the central line, how much at what point you are taking that, right? So we are taking it as X. Okay, so these are the two expression. And this expression small b is nothing but b by 2. That is the half width of the footing. Okay. Now what we can do, we mark some points. So as I said, we mark a point x naught. So what is x naught? X naught is the point from the center line at any depth z where the shear strength is the maximum. Okay, the shear strength is the maximum. So at any depth z, x naught is the point at which or the distance from the center line at which the shear stress is maximum. Okay, so obviously this x naught is a function of the depth z, right? So here you can see we have plotted, right? So here we have the depth ratio depth, and here you have the length ratio x naught by b and L naught by b, where b is the width of the footing. So we have plotted a, so what we can plot a curve, okay, is from where we can get the x naught by, because this is important to us. It is sheet written. Next also we have L naught. So what is L naught? L naught is nothing but the point or the distance, lateral distance from the center line at which the vertical stress reaches 0.0 times, okay, of the applied stress at the surface. So at the surface it is Q. So at any depth Z, at L naught distance away from the center line, the vertical stress reaches a 0.01 Q value. Okay, 0.01 Q value. So that also we can plot using a curve. Okay, that also you can represent using a curve. So that for any depth z, we can find out the value, this value of x naught as well as m naught. And failure modes 2 and 3, the bearing capacity is dependent on strength of the reinforcement tiles. So in failure modes 2 and 3, the bearing capacity is dependent on the strength of the reinforcement. So we can see here TD. TD is nothing but the reinforcement force. Okay, the reinforcement force should be less than Fy. Fy by factor of safety is related to Fy, and Fs divided by factor of safety related to Fx. Now, what is Fy? Fy is the yield strength of the tiles. Okay, okay, yield strength of the tiles. That means it depends upon the material of the tile. So what Vinkatalli did, Vinkatalli actually used this to see. they express this reinforcement force as function of both yield strength of ties and also the pull-out resistance. Okay, so Fy is my yield strength of the ties and Ff is the pull-out resistance. And both these Ff and Fy are divided by some factorial shift. Okay, now Td Z comma N means the reinforcement force in each layer at each layer equal to reinforcement force when only one layer is present divided by the total number of layers. Okay, just is it is a way of representing. Okay, reinforcement force in each layer is equal to reinforcement force when only one layer is present divided by the total number of layers. Okay, now you can see here, say we have this stress distribution, that is Q naught or Q, that is active. Okay, the stress distribution is there at the ground level. And at any depth Z, we are making a soil, what to say, soil section. Okay, we are considering a soil section. Okay, soil section AD or ABCD. Okay, soil section ABCD, we are considering at any depth Z. Now, this ABCD, at the top surface of this ABCD soil section, the force that is acting is marked as FB top, which is a function of Q as well as one force will be acting, which is equal to FB bottom. FB bot is also a function of Q and Z forces it. Okay, thickness of this soil section is taken as delta H. Okay, okay. Now SQZ, SQZ is nothing but the SQZ is nothing but the shear resistance. Okay, the shear resistance that is developing. Okay, so SQZ is nothing but the shear resistance that is developing at this level, and TDZN is nothing but the what? Nothing but the tensile force or the strength or the reinforcement force that is developed. Okay, now you must be wondering that the reinforcements are applied like this, like laterally. Then why are we considering this TD and S both as vertical? Okay, why are we considering? So S is vertical is fine because we are considering this surface, right? This surface. So in that surface, we are considering the shear force, shear resistance. So it is fine. S is vertical, it is fine. But why are we considering TD as also vertical? So TD should be horizontal, right? Because the reinforcements are placed horizontally, isn't it? But the thing is, it is assumed that so this is the locus of the maximum shear forces, right? So, and at these points, it is considered that at the points of the intersection of the locus and the strips or the reinforcement, it is assumed that there is a kink that develops. Okay, there is one vertical kink that develops. So, due to this vertical kink, you can see that what happens. This T force, the T force at here it is horizontal, but at that point due to this kink, this becomes vertical. So that's why we are considering is vertical source. Understood, right? So instead of being straight at the point where it is intersecting, we consider that there is like this, some kink is there. Okay, some vertical, that some kink develops at the point of intersection. Okay, the reinforcement force is vertical at shear surface. It is only at these surfaces, these points, and horizontal everywhere else. Okay. Now see, now at this point, what? This point is what? X equal to X naught. X naught is what? X naught is the point where the shear stress, the shear source is the maximum. Okay. And also we have this X equal to L. So L is, okay, X equal to L. L also, you know, L is the point where we have this much force, this much vertical. All right. Okay, so here vertical stress acting, we have considered a soil section of depth delta H. Okay, at the top of the section, we have FV top acting. At the bottom, we have FV bottom acting. At the side, we have a shear resistance acting. The it is S. And also, we at the sides, at that particular point, the reinforcement forces are considered vertical, and that is TT. Okay, and x equal to x naught. X naught is the point where the shear stress is maximum, and x equal to L is the point where we have 0.01 types of Q, vertical force. Okay, so remember this is very important. Ties are assumed to have a vertical Q. And that's the only reason we are considering the tensile forces, the reinforcement forces as vertical at that. Now what we do, the equilibrium of the element ABCD in unreinforced soil and reinforced soil with single layer of reinforcement may be expressed as follows. So we are considering that in the soil there is only one layer of reinforcement, and for that we are writing the equation. Okay, the equilibrium equations for the unreinforced case and the reinforced case. Now for the unreinforced case there will be no TD, and for the reinforced case there will be TD. Also, one thing you see that this equation 4 is for the unreinforced case. So in unreinforced case, we have Q naught. Q naught is the initial bearing capacity. Okay, and Q. And for the reinforced case, the bearing capacity should increase to Q value. Okay, so that's why you are writing it is everything as a function of Q. Okay, so unreinforced it is a function of Q naught, and for reinforced it is a function of Q. And in unreinforced, you do not have the TD function, but for reinforced case, we have the reinforcement force TD. Yes. The force developed in the soil at the bottom surface, if this FB bottom is same in both, we can consider that it is same in both reinforced case as well as unreinforced case. Okay, so you can consider that those will not equivalent. So now we combine equation 4 with this 4 and 5. This gives us this equation. Now, the only term in the equation 7 that cannot be evaluated directly for any given value of Q or Q naught and Z is the reinforcement force TT. The other terms may be evaluated by integrating the stress equation. So this shear stress, okay, this F, D, okay, all these things we can determine by integrating the stress equations except the term reinforcement force. Now the other terms, what you will do? So we will integrate and find out. So the top, FV top is nothing but QZ, Q function of Q and Z is summation 0 to x naught sigma z dx. Okay, just we are integrating the vertical stresses from 0 to x. Okay, from 0 to x naught. So. Okay, similarly, the reinforce the shear force how to calculate. Again, we will multiply sigma tau xy, which is the shear stress, is a function of x naught comma z times delta h. Okay, so we have FV top Q, which is a function of Q and Z. We can write it as a function of J, which we can write it as J times Q into B. Now this J is a function of Z by B. Okay, J is a function of Z by B. And what is J? It is given in equation 11. Same the SQ we can write as I into Q into delta H. Now what is I? This I is given. I is a function of Z by B and is given by equation 13. So you can evaluate this integral 11, you can evaluate this integral 13, and then from 11 you can put here, you can get this V top, and this you can put here, you can get SQ. Okay, so that now what we can do is that so that it is easier for us to get the values of J, the integrals J and I, these integral values J and I. So what Binkett and Lee did, they gave this J and I as a function of Z by V in a graphical form. Okay, in a graphical form. So that directly from the graph we can obtain this. We will see that graph, okay, later. Okay, so now for now we remember that this J and I, which are essential for us to determine the FP top and the S respectively, are given in graphical form as a function of Z by V. There is a depth ratio. Okay, graphical form, and then from that directly from the graph we can find it out. So when we solve the problems, we'll get more clarity. Next we have theoretical and next what we do is that same thing, same theoretical analysis we're continuing. The next what we do is that we substitute equations 3, 11, and 12 into equation 5, which gives us a tie force. Okay. So we get a tie force developed at Z due to applied load on footing expressed in terms of bearing capacity ratio. So this tie force, this TD, we express as a function of the bearing capacity ratio Q by Q naught. Okay, Q by Q naught. So you can see finally this TD is a function of J, I, and Q by Q naught. On J is a function of Z by B, I is a function of Z by B. So that's why this dt is a function of both Z and N. Okay. Now tie break or yield resistance gives us the allowable total tensile force. So what is the allowable for total tensile force? Allowable total tensile force that the tie can take is given by Fy is equal to W into Nr into T by into Fy by Fs. Now, what is W? W is the width of a single tie. So we are considering strips. Okay, ties, steel types, strip ties. We are considering. Okay, that's why we are calling it. We are doing it for that. Steel strips. Okay, we are considering steel strips. Reinforcement with steel strips. Okay. So W is the width of a single tie, T is the thickness of the tie, NR is equal to number of ties per unit length of the footing, Fy is equal to yield strength of the reinforcement material, and Fy is the factor of safety on the yield strength. Now W into NR represents the total width of ties per unit length of the footing. Okay, means the out of plane direction. What is the total length of ties per unit length? It is represented as the linear density of reinforcement LDR, which is W into NR. The tie force TD needs to be compared to the yield strength Fy to assess the tie failure. Okay, so remember the tie force TD needs to be compared with the yield strength Fy to assess the tie failure. So when you will see when we solve the problems, you will see. Just like this, you are considering steel strips that are placed. Okay, steel strips in a place that you are considering. Okay. Yes, okay, is understood. Now, this TDU found out. The next thing that we found out, I have to find out is the pull-out capacity. Where is the FF? That is the pull-out capacity. Now, how to find that? The pull-out frictional resistance. The pull-out frictional resistance. F F requires the requires the evaluation of the total vertical normal force FB on the length of the reinforcement beyond the shear surface. Yeah. So how can we determine the FF? For FF, we have to determine the FB on the length of the total. It is the total vertical normal force. Now, from where can we get the total vertical normal force? Total vertical normal force we can get by integrating the vertical stress. Okay, vertical stress. So now, from where to where shall we integrate? So from where to where shall we integrate? So we have to integrate from this point to this point. Okay, L not to X naught. Okay, because this is the point, this is the length that actually lies beyond this rupture plane, rupture surface, beyond this rupture surface. So that is our embedment length. So that is our embedment length. So what we have to do, we need to calculate this pull out force at this region, right? Because that is the length which will prevent the pull out. Okay, because that is the anchorage length or the embedment. So we need to integrate in this part of the um, reinforcement. Hence, we are integrating from x naught to L naught. So L naught is the distance from the center line where S sigma b reduces to 1% of the applied pressure. Okay, issues. Now FV, you can write it as LDR times B times P is the width times M into Q. So M is another function with another function of Z by V, and this M can be found from got from equation 19. So M is equal to this integral. Okay. Okay. So M EF. So the vertical forces this part. EF we are calculating, right? We are calculating the vertical stress at this level. EF. Okay. This is my EF, right? EF. Yeah. Okay. Okay. So just give me a second. Okay. So we get this M. Now this FNT we can write as a VV plus LD R times gamma times L naught minus X naught times Z plus B. That is nothing but my what? Just we are adding this FV to the is gamma times X naught minus X L naught minus X naught times Z plus B. Okay. Just get that. Okay. Now then here one thing that I missed is there should be a term F here. Okay, this term F should be here. So now what is this F? F is nothing but the friction coefficient. Okay, friction coefficient. The vertical pressure you already calculated FVV. Then that time gamma times L naught minus X naught times the L naught minus X naught is the length, and what is the height? Height is the Z plus B. So Z plus B also we are considering, and then times F times gamma. Okay, just a second. Let me just check this one, sir. that can take skip it. Yeah, so yeah. So as I checked, yeah. So we have to have, right? Obviously, we have to have this friction coefficient F here. Okay, we have to have this friction in F here because it is FVB is nothing but from the pressure, vertical pressure that is coming, and my this term, as I said, is gamma times L naught minus X naught times Z plus P will give me the overburden pressure. Okay, overburden pressure that we are multiplying with the friction coefficient. Okay, then only it will be converted to the horizontal pressure. Okay, when we multiply the vertical pressure with the friction coefficient, then only it will get converted to the horizontal pressure, right? Okay, the frictional resistance of the frictional pressure F. That's why F term should be here. Okay, so this is the overburden pressure. So now if we combine this, finally we'll get this FF. So this importance equation is very important. So FF is given by twice F LDR bracket M times B times Q naught times Q by Q naught, where M is a function of Z by V. B is the width of the footing. Q naught is the footing pressure of the unreinforced soil. Q naught is the footing pressure, Q is the footing pressure of when the soil is reinforced, plus gamma L naught minus X naught. L naught, you know, the pointed lateral distance from the center line at which we have the lateral distance from the center line at which we have what? At which we have the vertical stresses 0.01 Q. Okay. And X naught is the point from the lateral distance from the center line at which you have the maximum shear stress. And Z plus D. Okay. So this should be Z plus D. Or Z plus D. Okay, so D is the depth of the footing. Okay, D is the depth of the footing below the ground level. So say we are having a footing like this. Yeah, okay, this is the ground level. So this is D. Okay, at any depth Z from here we are considering, right? So we are finding the total overburden pressure here. Okay, due to this side. Okay, at any level Z. Right. So remember. Therefore, the force developed in reinforcement layer TD is compared to the pull-out resistance given here. So this total force developed in the reinforcement layer TD have to be compared with this pull-out resistance Fa. Okay. For any given set of conditions, the reinforcement at force TD and pull-out resistance FF are functions of the ratio Q by Q naught, that is the bearing capacity ratio, while the yield force, it should be Fy. Fy is constant. Okay, Fy is constant. All right. So if you have any doubt till here, please feel free to ask me. Okay, you can ask me anytime, and I will be more than happy to solve your problem. So please see this properly. So I am doing it a little bit fast. I'm going a little bit fast. So I'm not able to less time with us. So what I suggest you is that if you have not, please feel free to ask me anytime. I will be more than happy to help you out. Okay. Again and again, I am telling you this. Yeah. Now, as I said, this I, M, and J, these are all our dimensional forces. These are expressed as terms of Z by B, depth ratios, and all these are expressed in a graphical form so that it is easier for us for any depth ratio. It is easier for us to directly get these values from the graph. Okay, it is expressed in graphical. All right, now what we are going to do, we are going to solve the problem. Okay, so main thing you have to remember is that this FF, this you need this, okay, you need this, you need this. So these things you need. Okay, these are the most important ones. Also this equation. Okay, even if you don't remember the derivation, it's fine. But these basic equations, it's important. What equations we need to design. Okay, we'll see. Let us see this question. Design a strip footing to carry a line load. Okay, you have to carry a line load of 1700 kilonewton per meter. The data for the design is as follows. Soil parameters are given. Soil parameters are given. C is 0. This position is 0. Phi is 35 degrees. Gamma is 17 kilonewton per meter cube. S is 30,000 kPa. S is the elastic modulus of the soil, that is 30,000 kPa. We'll see why we need this, and we have the Poisson ratio of the soil as 0.35. The reinforcement parameters are Fy is given as 2.5 into 10 to the power 5 kPa. Phi mu is 28 degree. FSY is 3. FSF is 2.5. Width of tie is 75 mm. LDR is 65%. Depth of foundation is 1 meter. Permissible settlement is 25 mm. And design life is 50 years. Okay, so these are given. Now this is a design problem, right? So this is a design problem. So what you have to make some assumptions, right? We have to make some assumptions. Since it is a design problem, we have to make some assumptions. Okay. Now, what are the assumptions that we have to make? You have to make assumption regarding the width of the footing. You have to make assumption regarding the depth of the first layer of the reinforcement. We have to make assumption regarding the spacing of the reinforcement. So these are the main three assumptions that we make. And one more important assumption that we have to make is the number of layers of reinforcement that we are going to put. So depth of the width, first is the width of the footing that you are considering, then the depth of the first layer of the reinforcement, then the spacing of the reinforcement layers, and the number of reinforcement layers. Now let us assume. So we are assuming, right? So this is it. Since it's design problem, first you have to start with some assumption. Let's assume B is 1, Q, that is the depth of first layer of the footing, is 0.5 meter. Then we have the delta H. Delta is in what? The spacing of the reinforcement layers, also at 0.5 meter. And we have the number of layers as 5 layers. Now U by B should be greater than 2 by 3, right? So it is fine. U by B is greater than So 2 by 3, right? So not meter should be less than 2 by 3, right? So U by B should be less than 2 by 3. Let us see. Start it for but U by B should be less than 2 by 3. Okay, so our U by B is 0.5. Okay, so it is less than 2 by less than 2 by 3. Right. So 2 by 3 is what? 0.67. But we have taken U by B as zero point 0.5, so it is fine, right? Okay, so your U by B is 0.5 by 1 is equal to 0.5, this is less than U by B, so it is okay. Now LDR is what? W times NR, right? Now, so my NR is what? 0.65, LDR is 65%, so 0.65 by 0.075, because 75 mm is the width of the ties. So 8.67 ties per meter length of the footing. Okay, 8.67 ties per meter length of the footing. Okay, so this NR I found. Okay, number of ties per unit length of the footing. So 8.67 ties we have to put per meter length of the footing. It is in the out of plane direction. You have to put 8.67, more than a nine, say nine number of 9 ties per meter length of the footing. Now let us find out the U and U. So it is gamma df Q minus 1 plus half gamma B and gamma. So you can even use your bearing capacity equation from the IS 6403. That also you can use, but not just for simplicity I am using this, but you can use that also. Okay. So gamma test 1047.2. Q net save is Q and new by a vector safety let we generally take it as 349 per meters. Okay, so this is from the bearing capacity equation. So next we have to find out from the, so what I will do. So for your NQ and all, I have actually given you the graph of this one. You can use this. Huh? Okay, and one more thing that we have to get this from the settlement rate. This is the elastic settlement equation. Just okay. So what we do, we generally take lesser of the two, right? Lesser of the two is the say bearing allowable bearing pressure. So what is the lesser of the two? One is 427.3 I free wave, another one is 349. So what will be my Q naught? My Q naught is the lesser of the two. It is 349 kPa. This is my Q naught. Now next I have to find the Q. Is what should be my improved. capacity. What should be my improved pressure? Okay. Of the for the when I reinforce the soil, how much pressure it should take, that I have to find out. So that is what 1700 by 1 is the width of the footing, should be 1700 kilometer per meter square kPa. Okay, it should be. But this is my Q naught and this is my Q. But this should be my improved value, right? So that's why I'm taking this Q. Okay, minimum this should be there. The next step for us is to find the TD for each of the layer. For each of the layer, what we have to do, we have to find out the TD. Okay, now TD, right? So how to find it? So let us what we will do. I will make a Excel sheet. We stop sharing from here. Share my screen. Okay, so I hope that it is visible. Now, the first thing is that we have considered 5 layers, and we have considered 5 layers are there. We have n total n. We have considered 5. So what is our target? Our target is to find the TD. This TD. Now, what is this TD? 1 by n z times b minus I times delta h times Q naught by Q naught minus 1. So what we are ultimately doing, is that we are finding all these terms, and then like so we are finding the TD. Okay, thus we are calculating the TD. Now for each layer we are finding out. So for us this n will be, let me show you. So this H is what? Delta H. This times delta H. Delta. Okay. Q naught by n. So what is my Q naught? Q naught by n. So what is Q naught? Q naught is 349. 349 by Q by Q naught. So yeah. So this number of layer is, so we have 270.2. So we have Q naught by n multiplied by Q by Q naught. Q naught by n multiplied by Q by Q naught minus 1. Okay, so we get 270.2. Okay, we get 270.2. This will be same for all the layers, right? So we'll just copy this term. Okay, 270. Depth of each layer. So the first layer we have decided we have decided the US 0.5, so 0.5, and all the other layers are also spaced at, so spacing also delta H we have also considered as a 0.5. So all will be just the we will add 0.5. That is the spacing also you have considered 0.5. So the depth is added. This is the depth of each layer from the base of the, right? Down like so. We have this now z by b. B we have considered taken as 1, so z by 1. Now we have J. Now what is J? So J is a function of this Z by B. J is a function of this Z by B. How to get J? J we have to calculate from this plot. Okay, J you have to find from here. Okay, J you have to find from here. First for 0.5, here. So what is the J? It is about here. Right, so how much you can take, you can approximately take. So I will be taking approximate values, but when you do it proper. Okay, you do everything proper. 0.35. Now for Z by B is equal to 1. What will be achievable? It will be here, so it will be less than that. Before now, for Z by B is 1.5 means here, take this value, approximate value here, we take, or same, huh? Send that by B as 2 here. Bit lower than that, you say, and then for Z by 2.5, if here, okay. Now we have what we have to do. We have J times B, right? We have J times B. So that we have to do J times what is my B? B is 1 meter. So same. So next is to find I. I again we have to find out from this plot. So again for Z by B 0.5, what is my I? Is about here. So approximately it can be 0.25. Z by B1, I is here. It is 0.18 approximately. Then 1.5, I is here. 0.13 approximately. So do it properly. When you do, you just take the scale and you measure everything. You do it. When Z by B is 2, it is here approximately 0.1. When Z by B is 2.5, it is here approximately 0.08. Now we have to multiply I times delta H. Delta H is the spacing. Spacing is 0.5. Values I get. Now the next is what JB minus I into delta H, right? So that we do JB minus I into delta H. You do right now. So finally, my whole term is 1 by n q naught into q by q naught minus 1. This you already calculated. So this times this value. This times value if you do, we get the TD. Okay, the TD. So you are seeing that as the depth increases, this TD almost becomes what to say, almost becomes your constant. Okay, almost gets constant. So, see why. Okay, so now you got that TT. So I will just copy it, copy and paste it in our PPT so that you can access it. Now my next target is to calculate the FF. Your next target is to calculate the FF. Now, how to calculate the FF? FF, I have to calculate FF. I need all these terms. I need all these quantities. So FF is 2 I LDR times M into B into Q naught Q by Q naught plus gamma into L naught minus X naught times Z plus T. So all these things I have to do. So all these things I have to do. So the depth of foundation is given in the question as 1 meter. Okay. So these okay. Huh? Now for layer 1, 2 into F into LDR. So what is F? F is not 10 phi, 10 of phi mu. Okay, 10 of not 10 of me, 10 of phi mu. Okay, F is 10 of phi mu, and phi mu is actually given our question, given in our question. Phi mu is 28 degrees. So 10 of 28 degrees, that is equal to mu. Phi mu is equal to mu. So it is nothing but F. So F is 10 of phi mu. So phi mu is given 28 degrees. So I will do 10 of 28. I get it as 0.5317. So it is 2 times F. F is 0.53171 times LDR. So LDR, how much did we get? LDR is how much? It is 65%. So 0.65. Okay, it will come as 0.691. Okay, so it will come as 0.691. Right now, for that, for the first layer, what is my Z? My Z is 0.5. What is my Z by B? Is also 0.5. What is my M? M M is a function of Z by B. Now, what do you have to do? What? Let me just write these terms for all the layers first. So, this first value. So, this first value is say same for everyone, right? Who is a well layer. Is same for all the layers. Now, Z is different. This one, this is 1, this is 1.5, this is 2, this is 2.5. Right? So Z is also I got. The next Z by B is 1, same 1.5, 2, 2.5. Okay, I got. Now next is my M. Now for Z by B 0.5, Z by B. So this from here I have to get the M. So for Z by B 0.5, what is my M? I can take it approximately as 0.125. Okay, now for Z by B1, what is my M? Here it is approximately 0.14. Now Z by B 1.5, what is my M? It is approximately 0.15. Again, for Z by B, how much? 2. Also, it's almost the same. It's almost 0.15 here also. And next again for this value 2.5 is also almost the same itself. Let us take 0.15 itself. So where do you do it properly? For just now for demonstration purpose, you can just take the values very fast. I am doing this. Okay. Now Q naught by Q naught. What is that? How much is that? So Q naught is 349 times Q by Q naught, Q is 1700 by 349. So ultimately it is nothing but uh, Q itself. So I will get 1700, right? Now what we do, we find this term MB, Q naught, Q by Q naught. This term we find out is M times B. B is 1 times this term, split like this. Okay, fine. Now next step is L naught by B. Now L naught I have to, you remember L naught and X naught. So L naught and X naught both are also a function of depth ratios. So L naught and X naught also I have to get from here, from this graph. Okay, so now it Z by B I have 0.5. So for 0.5, what is L naught? What is L naught by B? What is X naught by B? I have to get. So for 0.5, I have L naught by B as 1.55. Okay, here 1.55, and X naught by B as, surely here it will be 0.55. Then again, I have for Z by B 1, I have L naught by B as 2.6, and I have X naught by B as here 0.8. Now L naught by B for Z by B 1.5 here. Here we go here. It is 3.4 approximately. And for X naught by B here, oh, it's around 1.1. Now for 2, I have here close to 4, so 3.85 approximately. And X naught by B, I have near to 1.5, so 1.4. Then for 2.5, here again, approximately 4.2. Therefore, here I have approximately 1.65. Okay, so L naught by B, I got X naught by B. Now, what is L naught? L naught is nothing but L naught by B times B. So, this is my how much? 1. So, is that time. So, 1. Here you have, it's not these times 1. Okay, so I will give you this Excel sheets. Do not worry. I will upload this Excel sheet drive that I have shared with you. Okay, now next is L naught minus X naught. Okay, L naught minus X naught. L naught. Okay, so I will do L naught minus, sorry, L naught minus X naught at these values. Now Z plus D. So depth of footing is given as 1 meter, right? So Z plus D. Why 1? Because it is given in the question. Okay, now gamma times L naught minus X naught times Z plus D. So what is the gamma? 17. 17 times L naught minus X naught times 10. getting. Okay. So next is to find the FF. So FF is what? Equal to 2 times F into LDR is this times M into B into Q. That is this term plus gamma L this term. So it is 1 6. Let's put it. That is FF I got. Just for your sake, I will find out F here. Huh? F is 10. So now TD last is TD. I already found out here. So I will copy. So actually, now FSF I have to find out. FSF is FF by TD. So F I. These are the factors of safety. So if we so now my TD FTD should be less than or equal to my FF by FSF, right? So FSF we are finding out now, right? FSF will be what? FSF will be FF by TD. So that we are getting. So what is there any mention of FSF? So yeah, in the question it is given that the FSF is 2.5. So since FSF is 2.5, we need to ensure that all the FSF are 2.5. So here you can see that all the FF are 2.5. So these are fine. Okay, so these are all are good values. All are fine. All values are fine. All are now TMM. Now what is the thickness of the ties that is given to you? That thickness of the ties actually you have to calculate. Okay. Now when we calculate the thickness, so we had two conditions, right? If you remember, because Now, if you remember, we had this condition as TD should be less than Fy by Fsy and Ff by Fsf. Now, Fsf is if you take if you consider only this criteria, only that this right criteria. So from here you can get Fsf is nothing but Ff by Td. So Fsf we calculated this thing, and in the question it is given to us that the minimum Fsf should be 2.5. So we are getting all the FSF is 2.5, it is fine. Now the second criteria is criteria also we have to satisfy. So how do we satisfy that? We satisfy that by selecting the appropriate thickness. Now what is my thickness? The thickness of tie is given by FSY. FSY. So FSY, how much is FSY? It is given in the question 2.5 into 10 to the power 5. It's 2.5 2.5 E5, it is given in the question KPA FFFSY times TN means TD divided by LDR times FY. So what is my LDR? LDR is 65%, so 0.65. And what is my FY? What is my FY? So FSY is how much? FSY is given as 3. This factor here you have to put the factors. This is given as 3. And what is my FY? My FY is 2.5 into 2.5. Uh, I make some mistake. Just a second, let me check also. Seriously. Just give me 1 second. Check. Ah, understand. Array, see, everything is fine. Okay. Yeah, so this one I have to get in mm, right? So I have to multiply by 1,000. Yeah, guys. So 1.12 mm is my thickness. So this thickness, when I calculate, this satisfies this first criteria. This satisfies this first criteria. Okay. Okay, when I calculate this thickness, it's given. This FSY is given as 3 in the question. Okay, T is nothing but this T. Okay, LDR I have, FY also it's given in the question to us. Multiplies by 1,000 we are doing just because we need to convert it to mm from meters. Okay, now T design. Now, as per PS 8006, the British Standard 8006, the corrosion loss on each phase for 50-year service life is 1.35. Okay, on each phase, 1.35 mm is lost due to corrosion. Because we are using steel reinforcement, you need to consider this. So the corrosion loss on each phase for 50-year service life is 1.35 mm on each phase. Hence, the above thickness value should be increased by 2.7. So we'll increase this thickness value by 2.7. So what is my design thickness? So these are my design thicknesses. Okay. So we got the design thickness. You chose the design thickness of the reinforcement types that you are going to use. Okay. These are my design thickness. So these are the things that you need. Okay. I think. Now, what is the minimum length? The minimum length is the minimum length of the reinforcement. So if you remember, it was 2 L naught in one side from the center line through half side, it was L naught, right? So twice L naught will give me the minimum length of the reinforcement. Okay. Okay, in the minimum length of that line, minimum length of that line. So minimum length of this. So how to do that? You get 2L equal to 2 times L naught. Okay, so these are the minimum length of the lines. Okay, that you have to use. So you can take around 9 all ties, you can take 9 meters, that will be better. Okay. So this is how you have to solve the problem. So it is also step. Okay, so this we did. Okay. Now this is one design. So now what if we want to do, so this is fine. So now what you can do, you can try this problem by yourself by taking more different types of, say you can try how what changes. So if we took the width of the footing as 1 meter, na, right? So what if we take the width of the footing as 2 meters? So let us see. So now say let's all other things remain same. If say my B is 2 meter. Okay, then U by B is 0.552, is 0.25, which is less than 2 by 3. So, okay, now U and U will change, comma TF, and means 1 plus half, comma, comma. Okay, so this is case 2. Say, again, we are doing one more case. Say we choose B is equal to 2. 4 minus 1 plus 12 into 17 into 2. 52.4 come up as 7.6, okay, next equal to 140, 7.6 by 3 to 469.2, okay. Okay, so now my okay, so this is the QNS. Now from the settlement criteria, settlement, let us say settlement is also same 25 permissible settlement. So in that case, what happens? It's just to show you I am doing another trial. Huh? So from here you will get Q1 you will get 213.68. So my Q naught now becomes 213.68 kPa, and my Q will be 1700 by 2 now because width I have considered, width of footing I have considered 2. Yeah, rest other things let it remain same. Say width of the footing is 2, and rest all other things. Number of layers are same. The U is same, right? The spacing of the reinforcements are same. Rest all other things let it remain same. Now let us see what it is. How much time? So start it. So this we already did. This we already did. Next, everything is same. Now my Q naught has changed, right? It's 213. So it is 213.68 by 5 times Q by Q naught. What is Q? Q is 850 by 213.68. Will be 127 point. Now this rest other things I have kept same 0.5, 1, 1.5, depth is same, 2.5. Now Z by V will change. So because B is now how much? B is now 2. Z by V change. Okay, now my J, B, I, all these things will also change. I will just give right. I already did this. I will just give. So Z by V 0.25. So what is my J? Z by V 0.25. What is my J? Yeah. So J will be 0.35. Then again 0.35. So you do it properly. Okay, I'm just taking some rough approximate values. JB is J times B is 2. Again, I also have to select from this graph. I for 0.25. There it is almost 0.3. 5. Well, just approximate rough values. Okay. I into delta H times delta H is 5. GP minus IH. But TP is this times G. That copy is here. Now other things I am keeping same. So 2 times 0 point, how much was it? 0.5317. Some 7 times LDR. So 2 this is M also you have to get corresponding to ZY basis possible. That is our report. So now Q not given, is nothing but Q. It's 850, 50, B M into B is 2 times spelling this. Next I have L naught by B. So again, corresponding to Z by B, I have to get L naught by B and X naught by B from here. So that I will write the approximate solution. I think L naught is L naught by B times B. X naught is X naught by B times B. Okay, now L naught minus X naught, Z plus D, Z plus D is 1 meter. Things same. So gamma is gamma is how much? Gamma 17. So 17 times not minus X naught times Z plus D. Therefore, I get FF equal to this times this plus this. Right. So my FSF becomes FF. So we're seeing that uh, for this one, for this it's fine. This is fine, but for this one, I'm not getting the proper value. Right. So what we have to do, we have to redesign it again. Okay, we need to redesign it. To redesign. Yeah. This is fine. This is that is that fine. Okay. This for these also I will give it to you. You and For this case, we need to redesign it. We need to redesign it. So now what you can do is that stop sharing. Yes. You can give it to somebody. Share it to you. Next, what you can do is we did right. So next, what you can do, you can give one more try. Now, what you can do, you can change this U and also delta. Okay, so now this also you can do. So try cursor. You can keep the B same, or you can change the B, and you can give it a try by use. Okay, understood, right? So you can keep the B and same, and now with different delta H and U we can try, and n equal to 4. Can just try yours just for practice. You can see what changes are coming. So this is just optimization. Okay, you need to optimize the gap spacing, then the height and all this, the U, the spacing, the width of the footing, all these things you need to optimize. Okay, I'm not doing this again. Right. So now let us, we don't have much time. We have 20 minutes. So we'll just do this and finish it up. Sand grains you must have studied in your basic soil mechanics, right? So what are sand grains? So these are long tubular, what to say, long columns of sand that are actually constructed into the soil to accelerate consolidation. Okay, so accelerate consolidation. So what happens due to the sand drains? Due to the sand drains, the drainage path reduces. So if you do not have sand drains, so say the one water particle, so one water particle at the center, so it can drain like this, it can drain like this. So if you have double drainage condition, one water particle at the center would have to travel this much distance, okay, to drain. But now if you provide sand drains in the soil, the water particles that can also enter like this, like this. Okay, it can go right. So it can drain like this into the center. So together with the vertical, together with the vertical drainage, we also have radial drainage. Vertical, together with vertical consolidation, we also have drainage consolidation. So I am not going into the depth of this. So all of us have studied this on basic geotechnical engineering, basic soil mechanics. Just for revision, we are studying this. Okay. So sand drains are used for accelerated pre-consolidation. Drainage path gets reduced. Sand in the drains generally have 200 to 600 mm diameter. They should be at least 100 times, 1000 times, sorry, 1000 times more permeable than the native conditions. Okay, now so for vertical drainage, we know the time factor TV is well, CVT by D square, where D is my drainage path distance from the of the drainage path length. From there, time of consolidation can be calculated as TV D square by CV, where CV is the coefficient of consolidation. TV is the time factor. All right. Now, the blankets are also to be more permeable than the sand ring to drain away the water coming from the grass. The thickness of the sand blanket is generally 300 to 500. So what happens? So this is the case of a three-dimensional three-dimensional consolidation, right? So in one-dimensional consolidation, we only have the vertical drainage, but in three-dimensional consolidation, we have radial drainage as well as we have vertical drainage. So radial consolidation as well as the vertical. Due to the radial drainage and vertical drainage, you have the 3D consolidation. Okay, so we have radial drainage as well as we have the vertical drainage. So for that, the consolidation equation can be written like this. So CH dou square u by dou x square plus dou square u by dou y square plus CV dou square u by dou z square equal to dou u by dou t. So this CV dou square u by dou z square is the vertical consolidation or one-dimensional consolidation part, and CH dou square u dou x square plus dou square u dou y square is nothing but the radial consolidation part. Now, the average degree of consolidation UAV is given by 1 minus U UV minus 1 minus U R. So UV, capital UV is the degree of consolidation due to vertical drainage, and capital U1 is the degree of consolidation due to the radial. Now this we already know for vertical consolidation, this is the value of time factor. If U is less than 53% and if U is greater than 53%, then it will take 50%. This is the expression for the time factor. Okay. So time factor is a function of what? Time factor is a function of degree of consolidation. So time factor and degree of consolidation are related. So for time factor, degree of consolidation less than 50%, we have one time equation representing time factor, and for greater than 50%, we have another equation representing time. So these are time factor for vertical consolidation. Now for radial consolidation, how to find out this UR, capital U R? Now capital UR is given by 1 minus exponential minus 8TR by F is a function of N, where Fn is also given to you. Now what is TR? Now TR is nothing but a time factor for radial consolidation. This is CRT by DE square, where DE is the diameter of the unit circle area. N is the ratio of the radius of unit cell area by radius of the sand ring with N, and TR is the time factor. Okay. So now this UR, how to obtain this both this UR actually we can obtain graphically. Okay. There are graphs that are present, graphical representation of these equations that are present from where you can directly get this UR value. So okay, now let us solve an easy problem. So for with that it will be more clear. An embankment is proposed to be constructed over a layer of clay 10-meter thick underlain by an impermeable stratum. The embankment is 3-meter high and the field soil is a unit weight of 20 kilonewton per meter. The clay has the following properties. The CH is equal to 8 meter square per year, CV is 4.5 meter square per year, MV is 2.7 10 to the power minus 4 meter square per kilonewton. Sand rings of 400 dia are proposed to be installed in a square pattern at a spacing of 3 meters center to center. Determine the magnitude of the settlement that can be expected due to consolidation of the clay layer after 6 months of effective embankment loading. So how to do, so now how much is the effective stress that is being developed due to the embankment construction? That is nothing but the unit weight of the embankment times the height of the embankment. It is the extra pressure that is coming into the soil, extra effective stress that is getting developed into the soil. Due to this extra effective stress, what is excess pore water pressure are generated, and then this excess pore water pressure will dissipate, which will result in consolidation. 20 into 3, that is 60 kPa. I will do a little bit fast because these things are already you have studied in your soil mechanics course. Okay. So ultimate settlement SF is V times H times R into 2.7 into 4 times thickness times 60 is 0.162 meter, which is 162 mm. This is the ultimate, this is the total settlement that will happen. Now for vertical drainage first, we have TV CVT by H drainage square. Now CVT by 0.5. What is HDR? What is the, so clay is like this. Okay, this is clay. Here we are making embankment, and here it is impermeable. So drainage, vertical drainage can only happen in one side. So HDR is, this is given 10 meter, so 10 square. So this will come out as 0.0225. Now U is less than 60%. Generally take TPS 5 by 4 square. From here we have UV. We have 4 by pi into 0.0225. From here UV will get 0.17. So actually you are seeing that 17% is coming. So our assumption that U is less than 60%, and then we are using this equation. So our assumption of using this equation for TV is correct. So 0.17 here getting. Now for sand rains we are having radial consolidation. So dia of sand rain is given 400 mm. The radius of sand rain is 200 mm, which is 0.2 meter. Okay, now for square pattern of arrangement, for square pattern, we have radius, actual radius is 0.64 s, which is 0.564 times the spacing. Spacing, okay, spacing. 1692 meter. Now, what is capital R? Capital R is nothing but radius of unit cell area. RE is nothing but capital R, radius of unit cell area. So, my N is R by RT 1.692 divided by 0.2 will come out as 8.46. So my TR is RT by 4R square 8 into 0.5 by 4 into 1.692 square 0. Now, so as I said, this TR is related to this UR, that is a radial degree of consolidation. So this we can directly get from this chart. So for R is equal to 0.349, N is we got 8.46. So approximately, we have UR as 0.87. So from this chart, approximately we have UR as 0. Therefore, 1 minus U is 1 minus UV to 1 minus UR. So this we got a particle length is 17%, radial length is 87%. 1 minus U, that is 0.79. So my U will come out as 9. Okay, hence settlement of embankment. The end of 6 months is equal to, at the end of 6 months, how much? 8 into 162 equal to 144.5 mm. So only 162 minus 144.5, that is 17.5 mm settlement is going to happen after 6 months. So the maximum settlement, okay, 144.5 mm settlement out of the ultimate total settlement of 162 mm will accelerate and happen within the first 6 months only. So initially, say if you would not have constructed sand drains, you'd have taken say 10-20 years to reach this 10-20 years to reach this 144.5 mm settlement. But now this 144.5 mm settlement will be reached in 6 months, and after 6 months only 17.5 mm settlement will happen. Okay, 6 months, say I've taken 0.5. Okay, in terms of year. Right now PVD. So now we used sand rain for accelerated consolidation. For the same purpose, we can also use PVDs for pre-consolidation, for accelerated consolidation. So PVDs also I had shown you in the first class. I have shown you this arrangement, this construction, site visit picture I had shown you, right? So the PVDs actually have a geotextile filter layer outside. Outside they have a geotextile filter casing, geotextile filter covering, that is the white that you see, that is nothing but geotextile covering. And inside you have a corrugated plastic core. Like this, you have a corrugated plastic. So the function of the corrugated plastic core is to carry the water, to drain the water in the vertical direction. And the function of the geotextile covering, covering is that of a filter. That is, it allows water to enter into the plastic core, but it does not allow the soil particles to enter into the plastic. So this by section of a PVD is shown here. It is a length L and a thickness T. So typically 100 wide and 5 thick. Tensile strength 5 to 15 Newton. Typical discharge rate 2 to 5 liters per minute. Consists of drainage core and a filter cover all around. PVDs come in roll of about 100-meter length. They are pushed rapidly into the ground due to using these machines that are shown here rapidly to desired depth. Okay. Now, what are some problems in the sand drains? So, sand in the sand drains, they get clogged easily. And continuous drainage path is disturbed due to internal shear movement. So, these are sand columns, right? So, some movement, there is some movement. If there is something, these sand columns are trained to shear movements. Due to shear movements, what happens? The continuous drainage path of water is disturbed. It takes long times to install the sand drains. Yeah, comparatively to the PVTs, it takes a long time. Smear effect reduces drainage. So what is smear effect means? When you are constructing the sand drains, you are constructing the sand drains, the area just in the vicinity of the sand drains, area, so say this is a sand drain, right? We are putting the soil just in the vicinity of the sand drain gets disturbed. Due to this disturbance, what happens? Um, the permeability of that soil around the sand will get reduces. So the efficiency of the sand will get reduced. Due to this effect is called smear effect. It is the soil surrounding the sand will get disturbed and the permeability gets reduced. Now, what are the advantages of PVD? Continuous flow path even after shear movement because we have a defined corrugated drainage sheet inside. The water can easily flow. No clogging due to geotextile filter because if we have a geotextile outer covering, so there is no possibility of clogging due to soil particles. Then there is also some reinforcement action due to the tensile strength of the PVD. So the PVDs inherently have some tensile strength. So due to that tensile strength, there is some inherent reinforcement action. Okay. Now, these are the various patterns in which you can place PPT. So, we have the square pattern, we have the triangular pattern. Okay, so the diameter of influence in a square pattern is given by 1.128 s, whereas is the spacing between the unit cells, and diameter of the influence when you have a hexagonal pattern or triangular pattern of spacing is 1.05 s. The triangular pattern is found to be most efficient. Now, this Hans-Boas equation, you have a Hans-Boas 1979 actually used to find the time for consolidation using when we are using these PVTs. So time for consolidation T is given by D square by 8CH times ln D by D by 1 minus D by D square minus 3 minus D by D square by 4 ln 1 minus U bar. Now it is D and D, these are actually shown to you. So D is what? The diameter of the sand drain and equivalent diameter of this, not the sand drain, the PVT here. In our case, small d is the equivalent diameter of the PVT. Okay, equivalent diameter we have to find out from the thickness and the thickness and the width of the this thickness and the width of the from this L and T, this area we will calculate, and from there we will equate it to area of equivalent circle, and from there we can get the equivalent diameter of the PPT. And capital D is the diameter of influence area that is given here for triangular arrangement is 1.05 s, for square pattern it is 1.12 s. Now, if you neglect the small quantity d by d wholes, d by d square, you can write 3s this quantity, where u is the average degree of consolidation. So this way you can calculate the time required for testing. Okay. Now how you can get the D? We'll see. So let us, if we solve this problem, we'll see. Now PVD size is given to you 100 mm by 5 mm, means 100 mm width by 5 mm thickness. Okay. Consolidation to be achieved is 70%. Time available to us is 9. Coefficient of consolidation is given 10 meters square per year. This is my coefficient of consolidation. Time available is given in 9 months you have to achieve 70% and 70% consolidation. Now this remember this equation we are writing for consolidation only due to the horizontal drainage due to the PVDs. Okay, we are not considering vertical drainage. Vertical drainage is not considered. Just we want to drain using the PVDs. Okay, yeah. So first thing is that we have to find the equivalent what? Equivalent what? Equivalent what? The equivalent area. equivalent diameter, sorry, the equivalent diameter of the sand grain. The sand grain can be considered like this triangular. So where we have a width, we have a thickness, right? So what is the perimeter? 2W plus T. It can be equated to the circumference of a circle. Okay, so can I this 200 plus 5 is equal to pi d. From here I can get d as 66.84 mm. It is equal to 0.0668 meter. Okay. The next thing is next we are asked, we are given that the time available is given. So in 9 months we have to achieve 70% calculation, 70% consolidation. So what we are asked, we have to finally design the spacing and the pattern. Okay, design the spacing and the pattern of the PPTs. We have to design the spacing and the pattern of the PPT. So now my the time required is given to us in 9 months time. We have to achieve 70% consolidation. We have to design the arrangement of the PPTs. Okay. The time is written as what? D square A to CH by D minus 0.75 ln 1 minus 0. So 9 by 12. Okay, in terms of ER, I am writing d square 8 into 10, then d by 0.0668 minus 0.75, 1 by 1 minus 0.70. Okay, from here d square then by 0.0668 minus 0.75, 9 by 12 into 8 into 10, then 1 by 0.3, that is square. Ln D 0.0668 minus 0.75 equal to 49.335. So from here, what you can get? You can get D as approximately 3.88 meters. So what is D? Capital D is the what? Capital D is the diameter of the influence area that we got, right? Diameter of the influence area. Now what you have to do? We need to choose the spacing. Spacing we have to choose. So if we use square pattern, use weight 3.4 meter spacing, and if you use triangular pattern, then use 3.6 meter spacing, but a triangular pattern is more efficient. Okay, so with this we will end today's lecture, and tomorrow we will wrap up this course by starting the remaining two topics. That is, we will just introduce a little bit about the liners, and then it is basically geomembrane, and then we will and initially before that we will be solving some easy problems regarding drainage and filtration. Okay, so thank you so much for attending, and see you in tomorrow's session.